Dear colleagues, good day. Today we are going to talk about a very interesting topic related to the Counter-Unmanned Aircraft System, and we are going to talk about object detection models for devices with limited computing capabilities. I divided this presentation into three sections. The first one related to the main purpose of this research, the main ideas. The second one, of course, will describe in more detail two different machine learning models that we can use in a constrained device with constrained capabilities. And the last section related to conclusion about all topics. So what is this article about? It's some words about relevance of the problem. The study provides a detailed analysis and identifies the most common and powerful computer vision methods for detecting and identifying unmanned aerial vehicles. To be short, it's a UAV, depending on environmental condition from the perspective of using these models on low power computing devices on board an interceptor. The purpose of this paper is formalizing the most effective methods of UAV detection by analyzing existing approaches for today with regard to the real condition of particular UAV types, use from the perspective of using these models on low power computing devices on board of interceptor UAV. Some words about dynamic of UAV use. So since the start of the full-scale aggression against Ukraine, around 15,000 different types, especially it's a Shahed type, it's UAVs. So these type have been launched as shown in the previous figure. Even it's very light analysis of the data and the trends on this figure suggest that UAV attacks will continue to increase by the end of 2025. It's worth noting that these vehicles are used in combined attacks with different type of missiles to overload air defense systems. So it's very important to have some very cheap, very reliable system that can be used as a counter measure for such type of aircraft. Computer vision for counter unmanned aircraft system. The study focuses on the identifying and evaluating computer vision methods for detecting and tracking UAVs. This involves utilizing machine learning models to analyze images and videos, aiming to develop effective system. Model performance. The analysis considers the performance of various machine learning models in identifying UAVs in different environmental conditions, including two very interesting from my perspective, MobileNet SSD and fast object object, which was created especially for small devices. The study aimed to assess the effectiveness of these models for use in real-time detection and interception system. Let's start with the first model. It's MobileNet version 2. It's SSD FPN Lite. It's a model performance. This pre-trained object detection model identifies up to 10 objects in the image, outputting a bounding box for each detected object. It supports RGB, three color inputs at some not very big but enough resolution, and it's approximately 4 megabyte in size. It's actually not very small, but it's not very big and can be applied on board of small devices with constrained capabilities, calculating capabilities, but not for all of them. And the architecture is specifically optimized to work on devices with limited computing capabilities, which is achieved thanks to the lightweight mobile net version 2 base model. Accuracy during the training phase and testing, the model achieved an accuracy of 88%, mean average precision. It's about 77% during the training and 77% during the test database. It's not very high result, especially if we have a look at the test data set, especially if we take into account the importance of intercept tasks. We need to increase the number of epoch till 40 and setting the learning rate till 0.02, and it allows us to improve accuracy to the 86% on the test data set. So it's more or less good result, but it's this is only initial training of this model, and we started to study different ability of this model. The next one, it's a former faster object, more objects, mobile net version 2. It's this model based on mobile net version 2 is designed for constrained devices with a size under 100 kilobytes and support for grayscale RGB input of any resolution, and it's the main differences from the previous one to run on object detection models. FOMO is a groundbreaking algorithm that brings real-time object detection, tracking and counting to microcontrollers for the first time. The model achieved the accuracy at 97% during training and 88% on the test data set. It's a bit more than previous one, but the most interesting thing here that we have some inference features so that we can use this model on our constrained devices. Inference time it's more than 1 second. Peak usage of random access memory, it's about 3 megabytes. Flash usage it's more about 11 kilobytes, so it's very suitable for using on the different microcontrollers with constrained capabilities. Accuracy at the same time, of course, it should be noted that the detection accuracy decreased to the 84%. Of course, this is a price for reducing the precision of weights of this model in order to be able to apply this model on the constrained device. Challenges, I would like to pay more attention for the one big challenge. It's poor detection of large objects for grounds when the UAV is almost the same size as the house against which it was shot. The geometry of the house, the triangle roof, similar to the shape of UAV, etc., affects the detection, of course. This problem was typically for my mobile net SSD, and for the former model solved this problem completely. Sensitivity to input quality. Compact models are often more sensitive to noise, poor lighting, or unusual angles of objects, of course. Some words in these slides about salient object detection. It's a key approaches. Actually, frankly speaking, we did not go in. We didn't go into big details. We just make some very short research in order to combine or to clarify for ourselves all available methods, and this is a point or issues of our future research. Next, I'd like to support some combined system for UAV detection according to the condition in which these aircraft used. Usually it's night, during the night period of time. So it's very interesting to use a combination of two systems, at least infrared system, for example, and it's machine learning or machine vision model. And you can see on this picture the combination of the main common idea of how to implement combine system for UAV detection, recognition, and interception. And some word about tracking. Tracking is carried out by tracking a rectangular frame that was superimposed on the detected UAV at the previous stage, and targeting is performed by aligning the z-axis of the intercept aircraft with the center of tracking frame. This is the one more issue for the future research. And conclusion, some words about conclusion, only main points, because there are a lot of interesting results. As I have told before, we need to combine different methods to build a very effective counter-unmanned aircraft system. Solving the target detection problem and imposing the rectangle bounding box will allow to proceed to this vehicle tracking using one of the segmentation-based tracking methods, of course. And the result obtained regarding to the accuracy of detection and identification at the level of 90%, and small size of models allow to speak about the possibility of using the consider models on devices with a limited computing power. Of course, Raspberry Pi is a much more powerful platform than Arduino, for example, for deploying machine learning models, including such that we have seen before. Some words about FOMA. FOMA does not provide precise bounding boxes, only centroids and segmentation masks, and if precise object coordinates are crucial for the application, this can be a problem. So thank you very much for your attention.